Hello everyone. Today I'll be presenting the major concepts of Units 1 through 4, including the linear systems, analytic geometry, properties of quadratic relations, and applications of quadratics. So throughout this presentation, I will explain not only how these concepts work mathematically, but also how they can be applied to real-world situations. One important idea that connects all four units is that math helps us model relationships, analyze patterns, and solve practical problems logically and efficiently. So, why do we study these relationships? So math is much more than memorizing formulas. So, it helps us recognize patterns, predict outcomes, and solve problems in organized ways. So, linear systems help determine where relationships intersect. Analytic geometry allows us to study shape and positions using coordinates, and the quadratic relations help model curve patterns and changing rates. Finally, quadratic applications allow us to optimize situations such as maximizing profit or predicting motion. So altogether, these concepts show how math can be used to understand and solve real-world problems. Learning goals and success criteria. So, by the end of this unit, you should be able to understand what a system of linear equations represents, solve the linear systems using different methods, apply linear system to real-world situations, and you're successful when you can graph two linear equations accurately, identify the point of intersection, and lastly, solve systems using graphing, substitution, and elimination. Okay, so for the linear system, a system of linear equations is used when two different relations are compared simultaneously, and the solution to a linear system is the points at which both equations hold simultaneously. And graphically, this is represented by the point of the intersection where the two lines meet together. So linear systems are useful because they help solve real-world problems involving comparisons, costs, rates, and also decision making. There are multiple methods for solving systems, including graphing, substitution, and elimination. Each method has advantages depending on the situation, so you need to decide which method you're going to use when you solve the problem. So let's plot the values. The variable form a straight line like this, as you can see on the graph on the left side. So for the slope intersect form, the equation of the line can be written using the slope intercept form, which is y equals mx plus b. The m represents slope and the b represents the y-intercept. So it allows you to describe a straight line, calculate future values, and determine how a variable changes. How do you calculate the slope of a line? Slope describes the steepness and direction of a line. It is calculated using the formula run over rise, as you can see over on the right side. So let's calculate the slope. By using this formula that we just saw, you can just calculate like this. So rise, so it's run over rise, and the answer will be 2.06. How do you calculate the y-intercept of a line? The y-intercept is the point where the graph crosses the y-axis, and calculate the y-intercept by determining the value of y when x is 0. So let's calculate the y-intercept. Substitute the values of m equals 2.06 and one data point 1.00 and 2.26 into the equations like this. Then solve for b. So first you need to substitute m with 2.06 and x with 1.00 and y with 2.26, and the answer will be 0.2. The quadratic formula. So the solutions to a quadratic equation of the form ax squared plus bx plus c are given by the formula x equals 2a over minus b plus minus root squared b squared minus 4ac, where the a is unequal to 0 and a, b, and c are real numbers. The vertex form of a quadratic function. The vertex form of a quadratic function is given by y equals a bracket x minus h squared, this is the squared, plus k, where h and k is the vertex of the parabola. The standard form, a quadratic equation is in standard form if written uh, if it's written as ax squared plus bx plus c equals to 0. And it clearly shows the quadratic term, linear term, and constant term which are needed for the quadratic formula. So there's a quick quiz that we can solve together. So the question is, you start a business selling custom t-shirts. You need to know when you will stop losing money and start making a profit. Let X to the number of the shirts sold and let Y equal to the total money you earned in dollars. Okay. So the first equation represents the total cost of producing custom t-shirts. The business has a fixed cost of $200 for the printing machine plus $5 for every shirt produced. And the second equation represents the revenue because each shirt is sold for $15. To determine when the business breaks even, the two equations are set equal to each other because the cost and revenue are the same at that point. So after solving the system, the solution is 20 shirts and $300. This means the business must sell 20 shirts before it stops losing money and begins earning a profit. So graphically, this is represented by the intersection point of the two lines. This example shows how linear systems help businesses make financial decisions and predict outcomes mathematically. After solving relationships algebraically, in linear systems, the next step is understanding those relationships geometrically. Analytic geometry combines algebra and geometry by using coordinates to analyze distances, slopes, and relationships between lines. This allows mathematical relationships to be visualized spatially. Analytic geometry uses coordinates and equations to study geometric relationships. One important concept is slope, which measures the steepness and direction of a line. Midpoints help locate the center between 2 points, while the distance formula calculates the exact distance between locations. So, in this unit is important because it connects the algebraic calculations to visual representations. So, this example shows how analytic geometry can be used in navigation and city planning. So the distance formula helps calculate the shortest route between two locations, while the midpoint formula can identify a central meeting location. For example, emergency services and navigation systems rely on coordinate geometry to improve efficiency and accuracy. Using graphs also makes geometric relationships easier to visualize and interpret. Slopes help identify relations between lines. Parallel lines can have equal slopes because they rise and run at the same rate. Perpendicular lines have opposite reciprocal slopes, meaning they intersect at right angles, so which is 90 degrees. And visualizing these relationships on a graph made the concepts easier to understand because the patterns become more obvious. So this is the example of the volleyball player. So linear relations change at a constant rate, which creates straight line graphs. However, many real world situations do not change constantly. Quadratic relations model situations where the rate of change varies, creating curved graphs called parabolas. This allows maths to model more complex patterns such as motion and optimization. So, so when a player hits the ball, what path does the ball follow in the air? It actually makes a U-shaped or the arc-like path in the air which opens downward. Okay, so when a volleyball is hit, its path form a parabola. And quadratic relations are useful because they help model projectile motion. The vertex represent the maximum height of the volleyball, and the x-intercepts represent where the ball begins and lands. This example demonstrates how quadratic equations can describe motion accurately in sports and physics. In Unit 4, quadratic relations are applied to solve real world problems. Quadratic equations are especially useful because they help identify optimal values such as maximum profit or maximum height. This unit focuses less on simply graphing equations and more on interpreting mathematical results in meaningful concepts. A quadratic relation creates a parabola. Unlike linear graphs, parabolas curve because the rate of change is constantly changing. One important feature is the vertex, which represents either the maximum or minimum points. The axis of symmetry divides the parabola into two halves, which are equal, and the value of it determines whether the parabola opens upward or downwards and how stretched the graph appears. How to graph a quadratic function by plotting points. So first, make a table of values and choose integer values of x. Second, substitute each x value into the function to find the corresponding y value. Third, plot the ordered pairs on the coordinate plane. And lastly, draw a smooth curve through the points to form the parabola. The axis of symmetry is an imaginary vertical line that divides the parabola into two equal mirror images. This line always passes through the vertex of the parabola. The equation of the axis is x equal to h, where h is the x coordinate of the vertex. So this is the citations, which is APA. I got the ideas from, and thank you for listening. This was MPM2D Unit 4 AOL